Good morning. Welcome to the 35th lecture on economics, management and entrepreneurship. In our last lecture, we revisited forecasting methods. We elaborately discussed regression methods. In that, we had developed a vector matrix representation of the dependent variable y with a set of independent variables x 1 through x k, and we said that it is possible to estimate the values of the regression parameters beta 0, beta 1, beta 2 etcetera that minimize the squared error between the estimated values of the dependent variable and the actual values. We also said towards the end of the lecture that there are a few statistics that indicate the adequacy of the regression of the dependent variable y on the independent variables x 1 through x k. We shall to start with today discuss an example to illustrate the use of the regression method, and thereafter we shall discuss two methods of time series forecasting that are useful for short term projection of an independent variable. Let us take up the example first to illustrate the use of the regression method. Here is the example. Sale of a product is assumed to depend on price and average personal income. The values of these variables are given below for 5 cities, that is 5 observations are made in different cities. City 1, the sale was 10,000 rupees per year, where the price of the product sold there was only 2 rupees per unit, whereas the average personal income in that city was 20 lakh rupees per year per person. City number 2, sale was 12,000 rupees per year, the price of the product selling there was rupees 4, and the average personal income was 30 lakh rupees per year per person. So, like that in 5 different cities, 5 values of sale and the prevailing unit price of the product in each of these cities, and the personal income, average personal income of a person per year in terms of lakh rupees per year per person were also found out. So, this is the table of observations. Here we have assumed sale to be a function of price and income. That means, price and income are independent variables, are assumed independent, and sale depends on these two independent variables. Therefore, sale is the dependent variable or explained variable, and price and income are considered as explanatory variables. We are required to fit a regression line, that is regress sale on price and income. That means, find out the regression coefficients of the regression between sale and price and income. Find also the R square and T statistics. Now, if the price and income are predicted to be rupees 5 per unit and 80 lakh rupees per year per person, then what is the most likely sale of the product? This is the question. The first part of the question deals with estimating a linear relationship between sale and price and income. The second part of the question is, after we have established a relationship between these variables, use that relationship to project the value of sale of the product when price and income values are predicted to be 5 and 80 respectively. Now, from the given data, the observed value of the dependent variable, the cell, is y. Cell is basically y. The matrix of independent variables contain, the first column is 1 1 1 1 1, but the other two columns are the price figures and the personal income figures. Then we use our formula for beta, which is x transposed x whole inverse x transposed y. Now that we have the values of y and x here, the values of y and x are given here, we can use them here and find out a value. The value for beta is a vector that comes as 12.769 minus 3.692 and 0.362. Now, these values, these values are given here in this vector. Hence, the regression equation is y hat is equal to x beta hat, and from there we get cell equal to 12.769 minus 3.692 into price plus 0.362 into personal income. So, now that the beta values are given, beta 1, this is beta 0 12.769 minus beta 1 into price plus beta 2 into personal income. Now, these results can also be obtained, as I said, by using any of the standard software packages. One of the most well known package is what is known as SPSS. SPSS is one of the oldest software packages, statistical packages. There are nowadays a large number of statistical packages. However, now these results have been obtained by using SPSS, and the value of beta has been obtained as this. Hence, the regression equation is obtained as this, that is beta 0 plus beta 1 x 1 plus beta 2 x 2. In this case, beta 1 is minus 3.692 and beta 2 is 0.362 pi. Now, from this equation, the interpretation is that if there is a unit change in price, whereas these are held constant, the other variables like personal income remains as it is, but price increases by 1, then the cell will fall by minus 3.692. The reverse is also true. If price falls, personal income remaining same, then the value of cell would rise by 3.692. So, this negative sign indicates that there is a reverse causality between cell and price. If price increases, cell decreases. and the amount by which sale will decrease when price is given an increment of 1 is 3.692, when all other variables remain constant at their prevailing values. We can give a similar interpretation for 0.362. It says that price held constant at its prevailing value. If personal income rises by 1, then sale would rise by 0.36 to 1000 rupees per year. So, there is a positive relationship between sale and P/I, and the magnitude of change in sale for a unit change in P/I given price is constant, remaining constant, is given by the coefficients. So, these are the interpretations of the regression coefficients, which are in this case this and this. From our own observation also, we know that if price increases, in most of the product sale would fall, and if personal income rises, sale would rise. Thus, intuitively this relationship is adequate. However, there are statistical relationships also. Statistical estimates can be made of standard error of these estimates. Beta 0, the average value is 12.769 and its standard error calculated by the software package is 5.351, and the t statistic is this divided by this, that comes to, that is beta 0 divided by its standard error, that comes to 2.386. Similarly, the standard error in making the estimate of the values of beta 1 is 1.592, giving a t value of the ratio of the two, which is minus 2.322, and the average value is 0.362, that is the estimate. The standard error of the estimate is 0.149, and the t value, this may be a little erroneous, I think it is, because 0.362 divided by 0.149 would be a little different, maybe 2 point something and not 0.149. This may please be corrected. I can't calculate it right now, but it appears that there is an error, and I have to wait for the values. I have forgotten the values, it is not coming. Oh. Yeah, this value will be 0.362 division 0.149. So, this will be close to 2.43. So, let me make this correction. This will be close to 2. So, it has not taken this value, but anyway this value is going to be 2.43, it is not taking. Okay, now it has taken. The t value is 2.43. Now, basically this you can see that the standard error being less than the actual values, the t values are higher, and this means that the beta values are not significantly different from 0. These are the interpretation of the standard error values and the t values. If the t values would have been less, it would have indicated that the values of this are close to 0, and if they are close to 0, it means suppose that the t value for p I was to 0 or close to 0, it would mean that this coefficient is also close to 0. It means that the personal income is not an explanatory variable, it does not explain cell, but because it is high, it means that this also is different from 0. This means that personal income does have an influence on cell. Now, I also introduced another statistic called R square statistic. In this case, the software SPSS gave a value of R square as 0.775 and the adjusted R square value came as 0.550. We would rely more on adjusted value of R square. 0.55 means that 55% of the variation of the actual values from its average was explained by our regression method. 55% is not very good, it only means that there are other factors that are at play and that influence the cells. Our initial assumption that price and personal income alone are the main factors that govern the variation in cell perhaps needs to be relooked into, and there may be a few other factors that are governing the variation of cell. The other factors could be the competitive products, for example, or price of competitive products. This could be another example, another explanatory variable. And if we now that we know that the R square adjusted value is just 0.55, it now tells us that we should look for such other explanatory variable, and if it is that the price of a competitive product is playing a role, then find its value and take also that. Therefore, we then have 3 explanatory variables: the price of this product, price of the competitive product, and on top of that the personal income. So, it is a 3 explanatory variables which are explaining the variation of cell. But assume that this is our estimated relationship between cell and price and personal income, which is reproduced here. The second part of the question says that suppose the predicted price is 5 rupees per unit and personal income rises to 80 lakh rupees per year per person, then what is the likely cell? What we need to do is just to put the value of these predicted values, price equal to 5, P I equal to 80, and that gives us a value of 23.269, and they are 1000 rupees per year, and therefore, this is 20,269 and not this 1000 again, this is a mistake, this is 23.269, thus this should be just 23. Oh, I am sorry, there is a problem here. it is not responding very fast. I must be careful. Okay, now that it has come. So, we have through this example understood how to formulate a model, how to estimate the coefficients of a regression model, and then how to interpret the values of the regression coefficients and their signs, that is plus or minus, and how to interpret R square and t statistics. Now, these are the very fundamental requirements for any regression analysis. Regression methods and econometric methods are very well developed, and one has to study much more in detail to get to know the other nuances of this interesting and very useful method. Now, we go to time series forecasting method. Time series forecasting methods, if you recall, are useful for short term forecasting. Short term forecasting is needed for production planning, for inventory control, and for working capital management and such other things. So, we should first of all understand the components of time series. Please recall that time series means that we have observed a particular variable x t for various values of t. This is called a time series. Observe values of x at different points of time. Now, normally a time series will have 4 components, although I have written 5. 4 components, the first 4 components, it will have an average, it will have a trend, a seasonality, and a random noise. These are, all of them are independent of each other. Autocorrelation is another component of time series, with the help of which one can find out whether there is a trend, whether there is a seasonality, and so on and so forth. Let us first of all study the meaning of these components. Before we do that, just one second. There is a lot of problem here. I am sorry, this whole thing is giving a problem. Yes. Now, I told you that there are 4 components of a time series. One is the average, the other is the trend, third is seasonality, and fourth is random noise. There is also a fifth component, which is autocorrelation, with the help of which you can understand whether there is a trend or seasonality or what. Now, let us see, this is a noisy time series. It means that this series has got noise associated with it, but of course, it has an average value such as this. So, this has an average value, this is an average value of this time series, this is x t and the x axis is time t, the y axis is x t, the value of the variable observed variable x at time t are these values indicated by the field dots, and we can say that it has a noise that is superimposed on this average value. The noise sometimes takes less value, sometimes takes more value, but on an average it has a value 0. Now, come to this particular time series. In this case, we can see that there is a long term trend over and above the average. The average is somewhere here, but there is a trend, or if we take this as the intercept A, then there is a trend here, and on top of that there is a noise associated on this. So, this is noisy time series with a trend. Now, look at this. This time series, you will see that there is an average which is here, and now it looks like there is a seasonality here. There is a regular pattern, up and down, upswing and downswing, upswing and downswing in regular interval. This, whenever there is a regular fluctuation with regularity, we usually call it a seasonality with a length of periodicity remaining constant. So, here we do not have a trend, we have instead an average, a seasonality, and there are small changes, and that is because of the noise present. The fourth one contains all the four components, such as the average, the trend, long term trend, there is a seasonality over the long term trend, and there are various fluctuations, because they are not exactly the same amplitude. So, that is difference in amplitude is because of the noise that is present. So, these 4 examples illustrate how a random or how a particular time series can be expressed in the form of its main 4 components. Now, we also introduced a component called autocorrelation. To understand autocorrelation, we have to first understand the meaning of correlation. As I told in the last lecture, correlation can be expressed to indicate linear relationship between 2 variables. Let us say the variables are x and y. If at a particular time we find the value of x and y, then, and suppose that we have, in this case we have taken 1, 2, 3, 4, 5, 6, 7, 8, 9 data points. For each data point we have x and y. So, this is the plot of x and y for the 9 observations, 9 sets of observations, and we find that this is on the rise. So, this is the probably the regression relationship between y and x, but the correlation coefficient is positive. This is expressed here in this manner. If they lie exactly on a almost exactly in a straight line, then they are 1 or close to 1. with a positive slope. If they lie on a straight line with a negative slope, then the correlation coefficient is -1, and if there is a slight deviation from linearity, but the trend is very high, the departure from the straight line is not very high, the correlation coefficient is 0.85. In this case, the correlation coefficient is -0.88. So, negative and close to 1. So, this is the meaning of correlation coefficient between two different variables, but we are dealing with only one, now this is another example that suppose the values of, we are now talking about autocorrelation. We have understood what is correlation. Autocorrelation is always discussed in only one time series. Let us say the time series is yt and the value for 9 readings are 10, 15, 20, 12, 14, 18, 25, 20 and 24. What we do? We take 1 period lag y values, we call it yt minus 1. That means, at time 2 we take y1, 2 minus 1 is 1, what was y1 was 10. So, yt minus 1 is 10, we write it here. At t equal to 2, we write the value of yt minus 1, that is 10. At t is equal to 3, we take the value of y2, that was 15. So, we write 15 here, 20 is written here, 12 is written here, like that, 14 here, 18 here, 25 here and 20 here. Now, this is like one time series y and this is another time series which is basically a lagged variable by 1 period lag. If we instead consider yt minus 2, then when t is equal to 3, 10 will come. So, 10 will come here, 15 will come here, 20 will come here, 12 will come here. So, we shall have another time series, that is basically yt lagged by 2 time periods, and similarly we can have yt lagged by 3, by 4, by 5, by 6 periods. Now, suppose we consider only 1 period lag time series, that is yt minus 1, and then we can now find correlation between these 2 time series. So, this is the type of correlation that I have plotted here for time period when y is equal to 10, the value of yt is 15. When yt minus 1 is 15, the value is 20. So, like that they have been plotted. Now, this may have a correlation of something like 0.5, positive trend, but not exactly singular or linear relationship. So, it is something like 0.5. So, that gives the value of the autocorrelation between yt and 1 period lag y as 0.5, and similar such things we can find between yt and yt minus 2, yt minus 3, yt against yt minus 4, so on and so forth. Now that we have the correlation coefficients of, we call it normally rho as the correlation coefficient, and that is a function of the lag, call that lag as tau. So, if we take tau here, when this value is 0, it is 1, it is correlated with itself. When it is 1, it will be less, still 2, it will be still less. So, there will be some sort of a curve here. This curve is called correlogram. Now, this curve may take different shapes. If this curve takes a shape such as this, it means that there is a trend in y. If it takes a shape such as this, it means there is a seasonality. So, this is the meaning of autocorrelation. Now, let us go to our topic of time series forecasting. So, given a time series x t, t equal to 1 through n, we can find out its smoothed value by taking weighted average of each of the past data when the weights are all greater than 0 and they add up to 1. So, x bar n is the weighted average of x. For example, if x t is observed to have values 5, 12, 8, 20 and 10, and suppose that we take all its weights, each one of them is given a weight of 0.2, then 0.2 multiplied by 5 plus 0.2 multiplied by 12 plus 0.2 multiplied by 8 and all that, it gives us a value of 11. Thus, 11 is the average value of x t. But suppose the weights are different. Suppose that we give highest weight to 5, that is 0.5, 0.2 to 12, 0.2 to 8, 0.1 to 20 and 0 to 10. You can see that each one of them is higher than greater than 0 and they add up to 1, 5.5 plus 0.2 plus 0.2 plus 0.1 plus 0, it gives 1. So, these are also weights. The value, the smoothed value of x now becomes less than 11, it becomes 10.5. So, there are different ways to calculate smoothed value or average value of a time series by giving different weights. The only two conditions are each weight must be greater than or equal to 0 and they must add up to 1. Now, the first time series, this time series if you recall is having a average value a and superimposed on that is a random noise, let us call this epsilon t. Random noises are normally assumed to follow normal distribution with mean 0 and a constant variance. That means, it can go deviate from 0 by certain amount. So, the expected value of x is nothing but expected value of a plus the expected value of epsilon, and this being 0, it is equal to expected value of a constant a, which is a itself. Therefore, for such a time series, the best forecast at time n plus 1 is a. So, if by plotting this, suppose that this is n, we have plotted this and we have found that the best for model for this time series is x t equals 1 plus a plus epsilon t, that is it has an average and a noise, then the best forecast is the average itself. A is its best forecast. The smoothed value is the best estimate of a. Now, by smoothing we are basically trying to find out what is the value of a. Thus, the forecast at time period n plus 1 or t plus 1, the next period forecast is nothing but the average value of x calculated at this point of time. This is thus the forecast, very simple. Now, we introduce moving average method. Consider the time series x t equal to x 1, x 2 etcetera up to t minus n plus 1 and then x t minus 1 and then finally x t. So, we have given the present value as t and the past values as this. Now, consider the most recent n values. It starts from here, this is the most recent x t, the present value, and last n data points come to this. So, up to this we will not consider the previous values. So, up to this we are considering. So, if you are considering only these values, we have with us x t minus n plus 1 etcetera up to x t. Write it reversely, it will be x t plus x t minus 1, the previous value, and then the last nth value, which is x t minus n plus 1. What is its average? By giving a weight of 1 by n to each one of these, it will come to x t bar. So, this is the average value of the most recent n data values. Now, suppose we go forward by one time period. So, we will then have another time series data x t plus 1, and suppose that we still rely on only n data points, that means we shall delete the oldest data x t minus n plus 1, which was there earlier. We shall delete that, and we have added the most recent data one period. Now, that time has advanced by one period, it becomes x t plus 1. So, we are dealing with another set of data, the oldest data being deleted and the newest data being added. Therefore, the moving average, so we can now freshly calculate an average based on the fresh set of data. We call it a moving average, calculated at t plus first time period, and that we will consider the most recent data, one period old data and n period old data divided by n, and we can continue this process. However, one does not have to calculate this. X bar t plus 1 is equal to, we can now say x t plus 1 up to this and minus this. So, you will see that this is nothing but the past average plus the one x new data that is added minus the old data that was deleted divided by n. That means, you have to remember only the last average value and the one that you are deleting and the one that you are retaining or adding. If you know these three data points, you can calculate the new value of x bar t plus 1. Sorry. Now, I will give a small example to illustrate this point. Suppose that we have data points 3, 4, 5, 6, 7 like that, 5 data points. So, these are x t values. We are interested to calculate, this is time 1, 2, 3, 4, 5. So, we calculate x bar 5 as equal to 1 by 5, 3 plus 4 plus 5 plus 6 plus 7, whatever that comes to, which is equal to 5. Now, that next, suppose that the next value is 10, then x bar 6 we calculate as 1 by 5, 4 plus 5 plus 6 plus 7 plus 10. Which is equal to 32 by 5 6.4. That is what that is incidentally equal to the last average, which is 5 plus what has been added is 10 and what is subtracted was 4. Let us see whether it is coming that way. 6 by 5, which is equal to 5 plus 1.4, which is 6.4. So, this is matching. Now, we have seen that the average is being moved by one time period, that is why the name moving average. Now, if the time series consists of an average and noise only, it is expressed in this manner, then the moving average is the best forecast for the next period. That means you find out the x bar t, and that is the best forecast. If the time series consists of an average, a trend and a noise, then it is usually expressed in this fashion: x t is equal to a plus b t. This is the trend rising with time t and superimposed by a random noise. So, the m period forecast will be f t m equal to a t plus b t m, m period forecast. If one period forecast, it is just a plus b, two period forecast, it is a plus 2b, a plus 3b, etc. We write a t here because as new time period, as time advances, we estimate the value of a by taking another moving average value, that is a t. That is why moving average value changes, a t changes. We also will make an estimate of the trend b. How we do it? We are showing it here. Now, look at this case. Suppose that x t is given by 7, 8, 10, 3, 11, 10, 6 and 8. Observed at time periods 1, 2, 3, 4, 5, 6, 7, 8. Let us assume that we have used n is equal to 3. That means, based on these values, we calculate this value. Just one second, I think there is a problem here. এখানে একটু বন্ধ করবেন, বুঝলেন? এখানে একটু বন্ধ করুন। এবারে ঠিক আছে কিন্তু স্টার্ট করুন। To illustrate this problem, this approach, let us say that we have 8 period data for a time series x t. The values are 6, 8, 10, 3, 11, 10, 6 and 8, and let us assume that we have taken only n is equal to 3. So, if you take n is equal to 3, then 6 plus 8 plus 10, that is 24 divided by 3 is 8. That is the moving average calculated at this time point. And when we go to the next time period, we will not consider 6, but consider 3 in addition. So, we shall only consider 8, 10 and 3. So, if we take that, then the moving average of this time series with at period 4 is equal to 8 plus 10, 18 plus 3, which is 21 divided by 3, which is 7. Similarly, when time period proceeds or advances by one more period, then we will consider only 10, 3 and 11. So, this is 13 plus 11, 24 divided by 3 is 8, and next one is 3 plus 11 plus 10, 24 divided by 3, which is 8. Next 11 plus 10 plus 6, which is 27 divided by 3, it is 9. Like that, we can calculate the single moving average x bar t. And what we have said, that suppose we assume that the forecast made for next period is the moving average calculated today, then forecast for the next period, when we have calculated the moving average as 8, the forecast for the next period is taken as 8. That means, we have initially assumed that this time series contains only an average and a noise and no trend. In that case, the best forecast is the moving average value for the next period. So, forecast for the next period is the moving average value made today. So, 8 is appearing here, 7 here, 8 here, 8 here, 9 here. Now, here we find that there is a forecast error. Now, this forecast error will also be different this forecast error is x t minus f t. In this case, x t is 3 and the forecast is 8. Therefore, the value is 3 minus 8, which is minus 5. The next forecast is 11 minus 7 is the error is 4, 10 minus 8 the error is 2, 6 minus 8 the error is minus 2 and like that. So, this is the forecast, and the forecast error is x t minus f t, which is this. So, we are trying to say that whenever we are trying to make a forecast with moving average, there will be a forecast error, and that this is the way to use the moving average method. And we will try to see how to use various alternatives to single or single moving average method. Thank you for today.